Let's discuss question 3 of the 2022 paper. A very interesting question, very unlike some other questions that have come in the previous years. A series of pipelines is installed to allow for the flow of storm water from the holiday park. The capacity of these pipes is given in liters per minute and is shown in the directed network. So the first question says, when considering the flow of storm water through this park, how many different cuts can be made? Many different cuts can be made. Determine the capacity of cut 1. That's relatively easy. You take all those cuts that go from the flow, from the sink to the source to the sink, and avoid those that go in the backward flow direction. So what I usually do is, yes, that's definitely going in the forward direction. This one is not. So I'll take that one. I'll avoid this one. This is another edge it cuts and its value is 15. And this is one it cuts, its value is 14. This one is a forward flow, 11, and this one is 19. And when we add all these, the value of these edges, we get a capacity of 74. Okay, so this answer to this is 74. The next question says, what's the maximum flow of storm water in liters per minute from the source to the sink? There are many strategies to get this particular answer. One of them is one method is to take all the paths and take the lowest value along those paths and add them up. Okay, the cut method. There is another method that we could use. Now, if we look at 20 liters flowing through here, though 20 liters reach here, it's only 18 that can flow through, okay, and reach this vertex L. And 18, when it reaches L, only 15 liters of those 18 will pass through this particular edge and reach this point, okay, with the sink at vertex R. So we can clearly see that there are some backward flows, so just cancel them so that you don't confuse yourself with going across these paths to check the flow, forward flow. And the next one that we can take, so even though there is, let's say we have reached maximum capacity here, okay, and let's now look at this 35 liters. It can't go in this direction, and so a part of it will definitely could flow through that way, and the smallest value along that path is 10. So we'll assume that 10 liter, because 10 forms the bottleneck here. So 10, so 15 first went through, now 10 goes through. So 10 out of 16 and 10 out of 15 and 10 out of 19 and 10 flowed through from 35 along that particular direction. And so we can see over here that this has reached maximum capacity. Now, if we look at what other paths, so here there is still a capacity of 25 that can flow through. Now, if it went in this direction, let's say out of the 25, 10 went in this direction. 9 went in this direction because there is still a capacity of 9 left. If it flows here, 9 can flow through, but at this point there is no outlet. So it's no use taking that particular path. Now, if a part of it, because there's still 25 here, if we now take another path, let's say 25 reaches here, but 20 goes through here. And if it flows in this direction, it will still come to a point when there's no forward flow from that direction. So we can't take that path either. So now let's look at the remaining path that's left. The only one that's left here is this one. So in order to check out what the value of the bottleneck here is on this path, we can say there's still a capacity of 25 left here, but the bottleneck is the lowest value along that path, which is 19. And so we say another 19 flows through, 19 here, 19 and 19. And the maximum saturation has happened here. So 15 plus 10 plus 19 will give you a value of 44, which is the maximum flow. Now Joe would like to increase the maximum flow through this network, either by increasing or reversing the direction of flow through one pipe, or by increasing the capacity of one pipe. The direction of flow is reversed through one pipe. Now, the direction of flow is reversed through one pipe. So let's see which one we can have the largest increase. That's extremely important, because I'm sure if you reverse the direction of some of these edges which have a backward flow, you can actually pass some more stormwater through it. But which one of these edges, if reversed, would have the largest increase? Okay. Now, if you look at this particular edge or this particular edge, reversing them is really of no use, because the maximum capacity that has been reached is here. So, and 15 of it passes through, which means that there is still 3 that can pass through either this way or that way. Okay. So that is just a small value of 3. Now let's see if there's any other edge that can be reversed so that we can have a larger increase. Now we can see that there is one, that QP. Now if we did reverse this direction and cause it to change direction that way, very likely we could have a larger increase in the storm flow of storm water. Now let's look at how this happens. Now looking at this particular edge, okay, we have seen that 29 of 35 has already flown through. So that gives me 6 extra liters that can still flow through. Now, is it possible for it to flow through here? Yes, because 10 out of 19 has gone through. That gives us a remainder of 9. And yes, 6 out of 9 can definitely flow through there. And we don't go up this way because we've reached maximum capacity here. So is it possible for the 6 to flow through here? Yes, because we haven't touched that. 14, the capacity of 14 is still there. So 6 can go through along NP. And if we reverse the direction of QP, 12, yes, 6 can go through. And we come to the edge QR. Now 10 out of 16 has actually gone through. That gives us a remainder of 6. Yes, 6 can definitely go through and reach maximum capacity there. And so we would have an extra 6. So though along the other edges we had an increase of 3, reversing Q to P will give us an increase of 6, which is the largest increase. So you have to be careful over here. You have to write Q to P because that is the direction in which it currently exists. Okay. So to reverse it would mean that you have to write Q first and P next. Now the next question says the capacity of one pipe is increased. Now the pipe that should have its capacity increased to cause the largest increase in flow from source to sink is the pipe that runs from this vertex to that vertex, and its new capacity should be at least blank. Let's look at this question again. Now, as we discussed previously, 18 liters would reach this particular vertex L, causing this to reach maximum capacity. Now, we can take quite a few different paths. Let's look at this one, reaching the same vertex. 5 is the bottleneck here, so 5 would reach here, and 5 would flow through there, and 5 would go across here, and 5 here. Now, the other path that we could take after this is, what is it that could reach R? So this is basically the inflow at this point is 23. So if we increased this by 8 to 23, definitely that would have increased this value over here, which was initially 15, okay, to 23, and increase the flow. So the largest increase in flow from source to sink runs from L to R, and its new capacity should be at least 23. A more detailed video of this question has been posted in another video, so please have a look at that if you want more explanations as to why there are other paths which can accommodate flow, but we haven't considered them and only looked at LR. Thanks, bye. Let's finish part D of the holiday park question, which is posted. Parts A, B and C have been posted in another video, so there's just part D left. The holiday park has had some changes to its roads to accommodate the new cabin. The adjacency matrix. So what's an adjacency matrix? A matrix that shows all direct connections shows road connections between the office and each cabin. The new cabin H is included in the matrix. On the diagram below, add the new cabin H and any additional roads in the network. So one, you have to add the new cabin and any additional roads. So what I actually thought was the best way to do this is to look at the degrees of each of these vertices. And so that's 2. Now the interesting thing that I noticed is along the diagonal, which is the first thing you should see, there happens to be a loop at H. Okay, so when you add the new cabin H, you have to add a loop at it as well, and a loop counts for 2 in the terms of a degree. So when putting down all the degrees, we get 4, 2, 3, 4 connections here, another 4 here, and 2, and this one you have to be careful, 1, 2 plus 2 for the loop. Okay, so that is 4. Now look at your diagram and try and match it up to the degrees that you can see. So the office is 3, and I can see that there are 3. A is 2. Yes, I can see A is 2. B is 4. Yes, it's 4. C is 2. D is 3. I can see that there's only 2, so obviously there's one more. E is 4. There's only currently 3. So clearly you must have. And F is 4. Yes, I can see 4 here. And G is 2. Now H is 4. So we now look at the connections that H has. It has one with D and with E. So clearly all you have to do is connect this, mark it as H, but you have to be careful to put a loop at H which counts a degree of 2, and these two edges count as 2, which makes it